The last topic we want to cover is power factor correction. And to do that, we're simply going to consider first finding the complex power of the source in this circuit here. So there's a few different ways we can do this, but the way that we're going to concern ourselves with is first converting all of the impedances in this circuit to an equivalent impedance. And if we do that, we get an equivalent impedance of 21 minus J10 ohms, which is also equal to 23 with a phase angle of minus 25 degrees. And from that, we can simply find the RMS current. So we have our voltage of the source, and we know the current coming out of the source. We can then find our complex power for the source, given by the RMS voltage times the complex conjugate of the RMS current. Now our power factor is simply the cosine of the difference of the phase for the voltage minus the phase of the current, and it's about 0.9, and it's leading. And simply recall that the power factor is kind of like an expression for the energy efficiency. So a good power factor, pretty solid to have. And that brings us into an example where we want to consider this circuit here. So we have 110 volts with a phase angle of 0 degrees for our RMS voltage, and our impedance is simply 5 plus J10. So from that, we can get our RMS current, and we can find our complex power. So from that, we get a power factor that's equal to 0.45. And, well, this power factor isn't too great. So we want to look at how we can make the system have a better power factor. But we don't want to change the average power to the load. So we want this 5 plus J10 load to still be getting 500 watts for the average power. And we're going to shoot for the stars and say that we want a new power factor of 0.95. So the first thing that we really want to ask is, do we add or do we subtract components? Now, if we subtract components, well, we don't really have too much to subtract. We have a source and we have our load. Probably can't subtract either of those. So we're going to add something. What is that something? And how is that something added? Is it in series or is it in parallel? Well, let's consider the series case first. So if we add something in series with this load here, we're going to get that the current changes and the amplitude of the current is going to change, which means the power delivered to that load is also probably going to change. So that's probably what we want to avoid because we still want to deliver that 500 watts to the system. So series, probably not the option. What about parallel? Let's consider our second case. Well, if we have something in parallel, we know that we still have that 110 volts over this load, and that would mean that this parallel branch would still get 500 watts. You would get this J980 that comes for the ride as well. But the current through the load is still remaining the same, and so is the voltage, so that load is still getting 500 watts. But maybe the thing in parallel can increase that power factor a little bit. So the parallel idea is what we're going to stick with for now. And the question is, what do we add in parallel? So if we have our original circuit with our RMS voltage source, and we have our load 5 plus J10, we know that the power for the load is going to equal 500 plus J times 980, and that's going to be volt amps. We're going to add something in parallel, just call it Z for now. But we know that we want to increase the new power factor to 0.95, which means that the difference in the voltage and the current phases is going to be equal to 18.19 degrees. Now, from our complex power, which we can express as some amplitude with the average power and the reactive power, plus that tangent inverse of Q divided by P, well, we can set that equal to the RMS voltage times the RMS current times the difference in phase for the voltage and the current. So what we can say is that the tangent inverse of Q divided by P average is equal to phi V minus phi I. And from that, we can simply just rearrange this equation to be the following. And we know that for this system, that average power, that's going to be that 500 watts that we delivered. So the old reactive power was 980 volt amp reactive, but that new reactive power is 164 approximately. So the delta Q, or the difference between the old and the new, is equal to 816 volt amp reactive. So what does this really tell us? Well, if we look at our old system, we know that our source, the power from that was 500 plus 980 volt amps, and we delivered that to the load. And if we look at our new system, we know that that source needs to supply 500 plus J164 volt amps. We know that the load is going to take 500 plus J980. So if we have a node here at this junction, we know that this impedance needs to supply 816 volt amp reactive to make these equations balance out such that the power in equals the power out. Now, depending on the convention we prefer, we can either draw the arrow this way and say J816, or we can draw the arrow going into the load and have minus J816. Either one is fine. The only thing we really need to keep track of is that the impedance that we added supplies Q to the load, and that Q needs to be 816 var. So looking at the last video, where we looked at the power, complex power for a capacitive circuit, what we got was that the complex power was equal to minus J times the RMS voltage times the RMS current. So we have an arrow going down with a minus Q, or depending on the convention, we can have an arrow going up with a positive Q. So referencing above, that's exactly what we need. So what we can say is that we're adding some kind of capacitance. And we can write the impedance for the capacitor as minus J times XC, or 1 divided by J omega C. Either is fine. And we know that the current for the capacitor is given by 110 volts with the phase angle of 0, which is just our input voltage divided by that impedance. So we arrive at this term here. And we know that the complex power for the capacitor is simply the voltage times that current. Don't forget that we need the conjugate of the current. So there's a negative there. And we can simplify this as minus J times 110 squared divided by XC. So we get that as the complex power for the capacitor. We know that that needs to equal the difference we determined above, which is it's minus 816. So from that, we can simply solve for XC, or 1 over omega C, whatever you prefer. And then you get a relation for the capacitor upon some frequency. Now there's another approach, which is the graphical approach. And since we've gone through the mathematics, we can now do the shortcut. So if we have the S plane, or the complex power plane, plotted, where we have the imaginary axis and the real axis, we can plot the old complex power and the new complex power that we need. So if we plot the old complex power, we get this here, where we have P average, which was our 500 watts, and then the Q, or reactive power, we determined. And then we can also define our power factor angle there. Now we wanted to keep the average power the same, but we wanted to change Q. So if we plot our new S, or new complex power, we get this second line here, where now we have Q new and our new power factor angle. So what you get is a difference in Q, like we calculated before. And we know that that's going to be equal to the RMS voltage squared divided by XC, which is equal to omega C times the RMS voltage squared. Again, we get the same equation where we had the capacitance needed inversely proportional to the frequency. Or you can look at it with all of the information on the S-plane, where you can say it's equal to the average power, and then you have the difference of these tangents